Quantum Physics in 2026, The Observer Effect. There is a question so old it was carved into table stone before anyone thought to write it as an equation. Does the world exist when no one is looking at it? For most of history, that question belonged to philosophers. Then, a little over a century ago, physics backed into it by accident, not by searching for meaning, but by trying to understand light and metal and a wall with two small holes cut into it. What physicists found there was not a new particle. It was not a new force. It was a crack in the picture of reality itself. For 3 centuries, science had told a simple, confident story. The universe is a machine, and it runs the same way whether or not anyone is watching it. Stars burn in the dark whether or not there is an eye to see them. Rivers flow, planets turn, apples fall. All of it happening in plain, objective fact, indifferent to any observer. Then physicists looked closer, past the apple, past the atom, down into the quantum world, and the machine stopped behaving like a machine. Down there, matter hesitates. It refuses to commit to a single story until something forces it to. It exists before we ask as a whisper of possibilities. And the instant we ask, the universe seems to answer with one definite fact, as though it had been waiting for the question. This single, quiet discovery has occupied some of the greatest minds of the last 100 years, and they have never agreed on what it means. Some insist there is no mystery at all, just unfamiliar math. Others suspect they brushed up against the deepest secret the universe has to offer. Tonight we are going to follow that secret as far as it goes. Through a wall with 2 slits, through the strangest equation ever written, through cats that are neither alive nor dead, through 8 billion years of a universe with no one in it, and finally to a question that physics can pose but cannot answer. What does it mean for something to be real? We won't rush. There's no need to grasp every equation or memorize every name along the way. We only need to follow the thread, one gentle step at a time, from a glowing piece of metal in 1900 to the edge of everything we don't yet understand. Let's begin. Part 1. The cracks in a perfect universe. At the turn of the 20th century, physics believed it was nearly finished. Newton had given the world its laws of motion. Maxwell had folded light neatly into the elegant mathematics of electromagnetism. Thermodynamics was tidy, orderly, complete. A few physicists even said, without much exaggeration, that all the great questions had been answered, that what remained was mopping up, tightening a few loose bolts on an otherwise perfect machine. One of those loose bolts involved something almost embarrassingly ordinary. What happens when you heat something up? Heat a piece of metal and it glows. First a dull red, then orange, then a blinding white as the temperature climbs. This glow, called blackbody radiation, was easy to observe and, everyone assumed, easy to explain using the well-tested equations of the day. But the math refused to cooperate. According to classical theory, a heated object should radiate more and more energy at shorter and shorter wavelengths without limit, spiraling toward infinite energy in the ultraviolet range. Actual heated metal did nothing of the sort. Physicists nicknamed the absurd prediction the ultraviolet catastrophe, and no amount of adjusting the equations made it behave. The man who finally tamed it was a cautious, conservative German physicist named Max Planck, who had no interest whatsoever in overthrowing physics. In 1900, purely to make the math work, Planck proposed something strange. What if energy wasn't emitted smoothly, like water from a tap, but in small, indivisible units? Packets he called quanta. Plug that assumption in, and the catastrophe vanished. The equations matched experiment perfectly. Planck himself didn't believe he had discovered anything fundamental. He called it a mathematical trick, a patch he assumed some future physicist would smooth away. He had, without meaning to, lit the first match under classical physics. It would take a swaggering young patent clerk in Switzerland to actually start the fire. In 1905, his miracle year. Albert Einstein turned to a different puzzle: the photoelectric effect. Shine light on a metal surface, and electrons pop loose. Simple enough, according to the wave theory of light. A brighter beam carries more energy, so it should knock electrons out with more force. Experiments said otherwise. Brightness barely mattered. What mattered was frequency. Below a certain frequency, even blinding light did nothing. Above it, even a faint beam ejected electrons instantly. Einstein's answer built directly on Planck's quanta, but went further, and further was the whole point. Light itself, Einstein proposed, is made of discrete particles, later named photons. Each photon carrying a fixed packet of energy tied to its frequency. A photon below the threshold energy is like a key that doesn't fit the lock. No matter how many you throw at the door, it stays shut. One with enough energy opens it instantly. Light, in other words, was both the smooth, spreading wave Maxwell had described and a hail of discrete particles, depending on how you asked the question. This was wave-particle duality, and it offended the tidy categories of 19th century physics on principle. Things were supposed to be one or the other. Nature, it turned out, hadn't gotten that memo. Einstein won his Nobel Prize not for relativity, as most people assume, but for this, for showing that the most familiar thing in the universe, light itself, refused, had to fit inside a single box. 2 quiet papers. A conservative man patching an equation, and a young rebel taking the patch seriously. Between them, they had lit a fuse that would burn for the rest of the century, and it was about to reach a wall with 2 small slits cut into it. In part 2, 2 slits, an impossible pattern. Picture the simplest experiment ever devised. A wall. 2 narrow, parallel slits cut into it. A light source on one side, a screen on the other to catch whatever comes through. It sounds almost too plain to matter. And yet inside this humble arrangement sits one of the most unsettling results in the history of science. We learn to expect a certain answer from waves. Send an ocean wave, or a sound wave, through 2 openings in a barrier, and it spreads out from both, the 2 new wavefronts overlapping on the far side. Where 2 crests meet, they reinforce each other. Where a crest meets a trough, they cancel out. The result is a repeating pattern of highs and lows. Physicists call it interference, and it's the unmistakable fingerprint of a wave. Particles behave completely differently. Fire tiny pellets at a wall with 2 openings, and each one goes through exactly one slit or the other. No overlapping, no interference. Just 2 clean clusters of impacts on the screen, directly behind each opening. So, which is light? At the dawn of the 19th century, the physician and physicist Thomas Young ran the experiment with light and found unmistakable interference bands, bright and dark stripes, rippling across the screen. Case closed. Light was a wave. That verdict held for 100 years. Then physicists shrank the experiment down to its absolute limit. Instead of a continuous beam, they dialed the light source down until it fired a single photon at a time, one lonely particle, crossing the apparatus completely alone, with nothing else around to interfere with. Each one struck the screen and left a single dot, exactly as a particle should. But let the experiment run. Let 100 photons land, then 1,000, then 1,000,000. Each one, individually, entirely alone. And something impossible happens. Out of that storm of solitary dots, the interference pattern reappears. Bright bands, dark bands. The unmistakable fingerprint of a wave, built one particle at a time by particles that never met each other. When this result first surfaced, physicists didn't celebrate. They recoiled. Surely it was an equipment flaw, a stray vibration polluting the data. So they tested it again, and again, for decades, with ever more care and ever stranger materials. Electrons did it. Whole atoms did it. Eventually, entire molecules built from hundreds of atoms. Objects almost large enough to see under a microscope did it too, each one launched alone, each one somehow interfering with itself on the way to the screen. The only way to make sense of it is to accept something deeply strange. Before it lands, a single particle does not have one location. It is described by a wave of probability, a spread of every place it might be, all coexisting, all real in some sense, until the moment it's forced to choose. This mathematical description is called the wave function, and it does not tell you where any individual particle will land. It refuses to. All it offers is the odds. And here is the detail that should stop you cold. Those odds are perfect. The wave function is, without exaggeration, the most successful predictive tool ever built by human beings. Confirmed to a precision so extreme, it's like measuring the width of a continent and being wrong by less than the width of a single hair. Every laser, every transistor, every screen you have ever looked at runs on its accuracy. Now for the twist that broke physics wide open. Suppose we simply want to know which slit each particle actually went through. A perfectly reasonable question. We place a small detector at the slits, just to watch the doorway, changing nothing else about the setup. The interference pattern vanishes. The moment we obtain which path information, the particles stop behaving like a spread-out wave and snap into ordinary, well-behaved little pellet. One clean cluster behind each slit, no interference, no ghost of a wave anywhere. Turn the detector off, and the interference pattern creeps back. Turn it on again, and it's gone. The universe, it seems, behaves one way when we ask a question and another way when we don't. It's worth being precise here, because the language gets misused constantly. In physics, observation doesn't mean a person paying attention. It means a physical interaction, the quantum system becoming entangled with something larger, whether that's a human eye, a machine sealed in a sunless vault, or a single stray molecule of air. The particle doesn't respond to being seen. It responds to being touched by the world in a way that leaves a record. And that ought to have settled everything, made the whole affair perfectly ordinary. Instead, it opened a question physics still hasn't closed, one with its own name: the measurement problem. What exactly counts as a measurement? At what precise point does a haze of possibility resolve into a single hard fact? The wave function, left alone, evolves smoothly, predictably, like water flowing downhill. Nothing in that smooth evolution ever forces a choice, and yet the instant we measure, a choice is exactly what we get. The mathematics describes the fog beautifully. It describes the outcome beautifully. What it says about the moment the many becomes the one, that gap is razor thin, and a century of the finest minds in physics has never fully closed it. Part 3. The mathematics of Mabe. If quantum physics had a single, sacred text, a spell whispered through the whole theory, it would be the equation Erwin Schrödinger wrote down in 1926. By the 1920s, physicists needed a new language. Electrons were showing wave-like interference. Photons behaved like probabilistic ghosts. Newton's tidy laws of motion track a particle's exact position and velocity, predict its future forever. Simply stopped applying. Schrödinger's equation described something different. Not where a particle is, but how the wave function, that spread of possibility, usually writ 10 with the Greek letter psi, evolves through time. Picture it this way. Classical physics draws a crisp arrow through space. Here is the particle, here is its speed, here is exactly where it will be next. Schrödinger's world draws something softer, a rippling, shifting cloud that says the particle is most likely here, a little less likely there, and just barely possible somewhere else entirely. The equation tells you exactly how that cloud breathes and moves through time. And when you finally measure the particle, when you ask it, bluntly, "Where are you?" the cloud collapses. All that spread out possibility snaps down to a single point. Here it is, but only after you've looked. This turned out to explain something that had puzzled physicists for years. Why atoms don't collapse. Electrons carry negative charge, nuclei carry positive charge, and opposite charges attract. So why doesn't every electron in the universe simply spiral into the nuclei? Thus it orbits? Schrödinger's equation gave the answer. Electrons around a nucleus don't orbit like tiny planets at all. They settle into standing waves, stable, three-dimensional patterns of probability called orbitals. The soft cloud shapes you may have seen sit etched in a textbook. These aren't paths. They're presence zones, and they exist precisely because an electron isn't a simple, localized particle. It's a ripple in a sea of probabilities, and that ripple has a shape it prefers to hold. Sitting beside Schrödinger's equation, discovered the same decade, is a second idea just as strange: the uncertainty principle. Introduced by Werner Heisenberg in the classical world, you can know exactly where something is and exactly how fast it's moving, both at once, without contradiction. A radar gun clocks a car's speed while GPS pins its location. No tension between the two. At the quantum scale, that tidy clarity breaks down completely. The more precisely you pin down a particle's position, the less precisely you can know its momentum, and vice versa. Always. No exceptions. This isn't a limitation of our instruments. It isn't solved by better technology. It's stitched into the mathematics itself, a direct consequence of the same wave nature that produces interference in the double-slit experiment. A wave that's narrow and sharply localized in space is necessarily spread out and blurry in the frequencies that make it up. And frequency, for a quantum wave, is tied directly to momentum. Squeeze a particle's position down tight, and its momentum runs wild in response. It's less a rule about knowledge and more a fact about the fabric of the world. The tighter you squeeze the mist, the less of it stays in your hands. This isn't chaos, though. It's structure. It's the very thing that keeps electrons from spiraling into the nucleus and destroying every atom in the universe. An electron confined to a razor-thin space around the nucleus would have such wildly uncertain momentum that it would require infinite energy to stay put. Nature says no. Electrons hover not because they want to, but because the uncertainty principle simply won't allow anything else. Two equations, 2 decades, and together they gave physics its new grammar. Reality doesn't run on certainty. It runs on probability, tightly, precisely, mathematically defined, and never quite resolved until something forces the question. And part 4, both and neither. In ordinary life, things settle into one state at a time. A coin lands heads or tails. A light switch is on or off. Quantum systems don't play by that rule, and the name for their strange in-between is superposition. Flip a classical coin and it lands on one side the whole time. You just don't know which until it lands. A quantum coin is different in kind, not just in degree. While it's in the air, it exists in a genuine blend of heads and tails at once. Not hidden, not secretly decided, but actually, physically both, right up until the instant you check. The moment you do, the superposition collapses, the coin picks a face, and your measurement becomes the new reality. Before you looked, it wasn't unknown, it was undetermined. Superposition isn't a quirk physicists tolerate. It's become one of the most powerful tools in modern technology. A classical computer bit is either 0 or 1. A quantum bit, a qubit, can hold both at once, a genuine mixture rather than a coin flip waiting to be resolved. Link multiple qubits together and the number of states they can represent simultaneously grows exponentially. 20 qubits, over 1 million combinations at once. That's the raw material behind quantum computing, quantum cryptography, and the ultra-sensitive instruments now used to detect impossibly small shifts in gravity and magnetic fields. The catch is fragility. Superpositions are almost comically easy to disturb. A stray photon, a passing air molecule, the faintest vibration is enough to collapse the delicate, blend into an ordinary, classical outcome. Physicists call this decoherence, and it will matter enormously later in this story. For now, hold on to the image. A feather balanced on a pencil tip in a room where someone, somewhere, is about to sneeze. If superposition is one particle refusing to pick a side, entanglement is two particles refusing to have sides independently of each other at all. Picture two ordinary gloves, one left-handed, one right-handed, sealed in separate boxes and shipped to opposite sides of the planet. Open one box and find a left glove. You instantly know the other box holds the right one. No mystery there. The gloves were always determined. You just didn't know which was which. Entangled particles are stranger than that. They're not like pre-packed gloves quietly waiting to be revealed. They're more like a pair of gloves that genuinely haven't decided which hand they are, until the instant you open one box, at which point the other, no matter how far away, instantly becomes its opposite. Measure one entangled photon in Paris and find it polarized vertically. Its entangled partner in Tokyo becomes horizontal at that exact moment, with no signal, no delay, no possible channel of communication between them. Einstein detested this idea and called it spooky action at a distance. He believed reality had to be local, that nothing could influence something else instantaneously across a distance without some signal traveling between them. Cornerstone of his own theory of relativity. In 1935, along with Boris Podolsky and Nathan Rosen, he argued that quantum mechanics, if it really permitted this, had to be an incomplete. The theory that some hidden variable, some secret instruction set, must be quietly determining the outcomes all along, unseen. 3 decades later, physicist John Bell devised a mathematical test, now called Bell's theorem, capable of distinguishing quantum mechanics from any theory built on such hidden variables. When the experiments were finally run, again and again, with ever-increasing rigor, quantum mechanics won cleanly. No hidden variables ever turned up. Entangled particles really do coordinate their outcomes in a way no local classical explanation can account for, and the correlation holds undiminished. Across any distance physicists have managed to test, including experiments bouncing entangled photons off satellites hundreds of kilometers apart. Crucially, this spookiness can't be weaponized into faster-than-light messaging. The outcome of any single measurement is still completely random. You can't choose what result you get, so you can't encode a message in it. What entanglement gives you is perfect correlation without communication. Two coins flipped across the galaxy, each landing on a genuinely random face, yet somehow, impossibly, always opposite. Nature keeps her books balanced instantly, even when the ledger spans light years, and no one has ever fully explained why. Part 5. The cat, the vacuum, and the wall that is there. By the 1930s, some physicists were growing uneasy with how far their colleagues were willing to stretch superposition, applying the same rules that governed electrons to anything and everything without limit. Erwin Schrödinger, of all people, decided to make that discomfort impossible to ignore. His thought experiment is now the most famous image in all of physics. Seal a cat in a box with a radioactive atom, a Geiger counter, a vial of poison, and a triggering mechanism. If the atom decays, a genuinely random quantum event, the counter fires, the vial shatters, and the cat dies. If it doesn't decay, the cat lives. Quantum mechanics says that until the atom is observed, it exists in superposition, decayed and not decayed, simultaneously. Follow the logic all the way through, and the cat itself must inherit that superposition, not metaphorically. Literally alive and dead at once, according to the letter of the theory, until someone opens the box. Schrödinger wasn't proposing an actual experiment. He was needling his own colleagues, exposing what he considered an absurdity in taking quantum rules too literally at large scales. But the image stuck precisely because it captures something real. An unmeasured quantum system doesn't contain one hidden, secret answer waiting to be uncovered. It contains every possible answer, genuinely unresolved, until a measurement forces one to become actual. Around the same set of ideas sits another effect that seems, on its face, to violate common sense entirely. Quantum tunneling. Throw a tennis ball at a wall without enough energy to get through, and it bounces off. End of story. No exceptions. In the world of everyday objects. In the quantum world, a particle can approach an energy barrier it technically shouldn't be able to cross, and still, some of the time, simply appear on the other side. No breaking, no squeezing through a crack. The particle's wave function doesn't stop dead at the barrier. It tapers off like a whisper fading through a wall. And if that whisper still has some amplitude on the far side, there's a real, calculable chance the particle will show up there. This isn't a curiosity confined to physics labs. It's the reason radioactive nuclei decay at all. Alpha particles trapped by a nuclear barrier, they shouldn't classically be able to escape. Nulling free bit by improbable bit until, eventually, they do. It's the reason stars shine. At the crushing pressures inside a star's core, hydrogen nuclei still don't quite have enough energy to overcome their mutual electric repulsion. But tunneling lets a tiny fraction fuse anyway, and multiplied across the unimaginable number of atoms inside a star, that tiny fraction is enough to power every sunrise you've ever seen. And then there's the strangest nothing in the universe. The quantum vacuum. Empty space, it turns out, is never actually empty. Heisenberg's uncertainty principle applies not only to position and momentum, but to energy and time as well. Which means that even in a region where the energy should sit at exactly zero, it can briefly, spontaneously fluctuate. These fluctuations spawn virtual particles, flickering into being and vanishing again almost instantly. Too fleeting to observe directly, but very real in their effects. One of those effects has actually been measured in a laboratory. Place two uncharged metal plates extremely close together in a vacuum, just nanometers apart, and something should happen. Nothing. According to classical physics, there's no charge, no field, nothing to push or pull them. And yet the plates draw together. Between the plates, the tiny gap restricts which wavelengths of virtual particles can exist there. Outside, there's no such restriction, and the resulting imbalance in pressure gently pushes the plates inward. This is the Casimir effect, and it has been confirmed with remarkable precision. Even a vacuum, even nothing, has a texture you can measure. At part 6, the universe made of ripples. Before we go any further into the mystery of the observer, it's worth pausing to ask what, exactly, is being observed. Not in the philosophical sense yet, just physically. What are electrons, photons, and quarks actually made of? For most of the 20th century, the working answer was fields. Not particles first, with fields as an afterthought, but the other way around. In classical physics, a field is something that assigns a value to every point in space. The familiar example is the electric field, an invisible influence that tells a charged object how to move. Fields are smooth, continuous, and fill the universe like an invisible jelly. Quantum mechanics sprinkles uncertainty over that picture. Fields don't sit quietly. They fluctuate, buzz, and jitter even in the total absence of any real particles. Every field, electric, magnetic, gravitational, turns out to be quantum in nature. This is the heart of quantum field theory. Every particle you've ever heard of, electrons, photons, quarks, neutrinos, is not a tiny marble flying through space. It is a localized ripple, a bump, a brief excitation in a field that fills all of reality. Somewhere out there is an electron field, present at every point in space. When you observe what we call an electron, you're witnessing a specific, quantized excitation of that field, not a separate, self-contained little object. The electromagnetic field fills space the same way, and a photon is simply a ripple in it. Tune that ripple one way, and you get visible light. Another way, and you get an X-ray. Different notes in the same underlying instrument. This reframing explains things ordinary particle talk struggles with. How do particle collisions at facilities like CERN create entirely new particles seemingly out of nothing? Simple. Smash enough energy into a region of space, and you can jiggle a field hard enough to spawn a new ripple. What are antiparticles? The electron's shadowy twin, the positron. Just another mode of excitation in the same field with opposite properties. More symmetry in the rippling, nothing supernatural about it. Even the forces of nature are, in this picture, fields talking to other fields. The electromagnetic force arises from charged particles exchanging photons. The strong nuclear force comes from gluons binding quarks together. Gravity, if it can ever be successfully folded into this framework, would involve ripples in a gravitational field carried by a hypothetical particle called the graviton. Sorting the resulting cast of characters gives us the standard model of particle physics. The closest thing physics has to a complete ingredient list for the universe. There are two broad families of matter particles. Quarks come in 6 types: up, down, charm, strange, top, and bottom, and combine in 2s and 3s to build protons and neutrons. Nearly everything you can touch is built from just the lightest 2, up and down. Leptons include the electron and its 2 heavier, short-lived cousins, the muon and the tau, each paired with an almost undetectable partner called a neutrino. Ghostly particles so aloof that billions pass through your body every second without leaving a trace. Holding these matter particles together are the force-carrying bosons. The photon for electromagnetism, the W and Z bosons for the weak nuclear force, responsible for the radioactive decay that helps power stars, the gluon for the strong force that binds quarks into protons and neutrons, and the Higgs boson, confirmed experimentally at CERN in 2012, the visible signature of a field that gives many other particles their mass in the first place. Without the Higgs mechanism, the standard model describes a strange, nearly weightless world where matter never clumps into atoms at all. It's a remarkably compact recipe, and it works with breathtaking precision, predicting the outcomes of particle collisions, radioactive decay rates, and atomic structure with staggering accuracy. And yet, it's famously, admittedly, incomplete. It has no explanation for gravity, which is still described separately by Einstein's classical theory of general relativity. It has nothing to say about dark matter, the invisible material whose gravity shapes entire galaxies. It has no account of dark energy, the mysterious force accelerating the universe's expansion. All told, the standard model, magnificent as it is, accounts for only about 5% of everything that exists. It is, in the words more than one physicist has used, a complete theory of an incomplete picture. A puzzle finished on its own terms, while the box it came in shows a much larger image still only partly assembled. The crown jewel sitting inside this framework is quantum electrodynamics, or QED, the theory of how light and matter interact, and quite simply, the most rigorously tested theory in the history of science. Developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, QED predicts outcomes like the tiny magnetic strength of a single electron, correct to better than 1 part in a billion, the equivalent of measuring the width of North America to within the thickness of a human hair, and being right. Feynman's great gift was making the underlying calculation almost playful. His famous diagrams represent particles as simple lines, time flowing left to right, with every possible way an interaction could occur. However strange, however roundabout, added together to produce the final, precise answer. Nature, in this picture, doesn't just do the one thing that happens. It quietly explores every possible path at once, and the interference between all of those paths is what QED calculates. In Part 7, where the wordness hides. If quantum theory only mattered inside particle colliders, it would still be one of the great achievements of the human mind. But its strangest features, superposition, entanglement, tunneling, have quietly slipped out of the laboratory and into the technology we use every day, and, more surprisingly still, into biology. Start with computing. A classical computer is built from bits. A switch that is either off or on, 0 or 1, and nothing in between. Every video, every song, every message you've ever sent is, underneath, an enormous pattern of these simple binary choices. A quantum computer replaces the bit with the qubit, and a qubit, thanks to superposition, doesn't have to choose. It can hold a genuine blend of 0 and 1 simultaneously, not switching rapidly between them, but truly, physically both. Add more qubits and the power grows exponentially. 2 qubits can represent 4 states at once, 3 can represent 8, 20 can represent over 1,000,000, all held in superposition simultaneously. This isn't the same as brute force parallel guessing. A quantum computer doesn't magically check every possible answer and hand you the right one. It shapes the probability landscape of the qubits so that, when finally measured, the correct answer is overwhelmingly the most likely outcome to appear. Entanglement adds a second layer of power on top of this, linking qubits together so that operations on one can influence the state of many others simultaneously. Correlation, no classical machine can replicate. None of this comes easily. Qubits are almost absurdly fragile, and here decoherence, the same process that keeps your coffee mug from ever being in 2 places at once, becomes the enemy rather than the explanation. The faintest stray vibration, a whisper of heat, a wandering magnetic field can collapse a carefully prepared superposition before any calculation finishes, which is why many quantum computers are cooled to temperatures colder than deep space, isolated as thoroughly as engineering allows. Despite the difficulty, real hardware exists today, with tens to hundreds of qubits, some machines already demonstrating quantum supremacy, completing specific tasks that would take a classical supercomputer an impractical amount of time. Promising applications are already taking shape, simulating molecules for drug discovery and battery design, tackling optimization problems with too many competing variables for classical methods, and, more ominously, breaking the encryption schemes that currently protect the internet, which has already spawned a new field, post-quantum cryptography, racing to build codes that even a future quantum computer can't crack. Stranger still is the growing evidence that biology may already be using these tricks quietly without waiting for engineers to catch up. Take the European robin, a small migratory bird that navigates thousands of miles with uncanny precision. For decades, no one could explain how it senses direction so reliably. The leading hypothesis today is genuinely startling. A protein in the bird's eye called cryptochrome may host a pair of quantum-entangled electrons, created when light strikes the molecule. Their entangled spins appear to interact with Earth's faint magnetic field in a way that influences a chemical reaction depending on which direction the bird is facing. A living compass built, quite possibly, out of quantum entanglement, somehow surviving inside a warm, wet, chaotic cell, a place quantum coherence has no business lasting more than an instant. Plants may be running a similarly elegant trick. In photosynthesis, sunlight striking a chlorophyll molecule needs to deliver its energy efficiently to a reaction center where it can be stored. A naive, random hop from molecule to molecule would be slow and wasteful. Measurements instead suggest the energy explores multiple paths at once, as though the whole system is using quantum coherence to find the most efficient route. Less a marble rattling randomly through a maze, more a wave spreading to feel out every corridor simultaneously before settling on the shortest one. And even your sense of smell has a controversial quantum contender. The vibrational theory of olfaction proposes that your nose detects not just a molecule's shape, the frequency at which it vibrates, sensed through electrons tunneling across a receptor. The same quantum trick that powers nuclear fusion inside stars, potentially happening quietly inside your own nostrils. None of this is settled science. Quantum biology remains a young, contested field, built more on bold hypotheses and careful early experiments than on final answers. But the mere possibility is enough to reshape how we think about the boundary between physics and life. The same mathematics that describes an isolated electron in a vacuum chamber may also underpin the migration of a bird and the shimmer of sunlight captured by a leaf. Quantum effects, it seems, were never locked away in a laboratory vault. They may have been here all along, quietly doing the work of living things. Part 8. The experiment that reaches backward. Before we dive fully into the measurement problem, there's one more experiment that deserves a place in this story because it takes everything we've established so far. The wave, the particle, the vanishing interference pattern, and adds a final twist that makes even seasoned physicists uneasy. It suggests the decision to look might somehow reach backward in time, return to the double slit. We already know the rule. Watch which slit a particle goes through, and the interference pattern disappears. Leave the path unknown, and the wave pattern returns. In the 1970s, physicist John Archibald Wheeler pushed the idea further with a proposal called the delayed choice experiment. What if you didn't decide whether to measure the particle's path until after it had already passed through the slits? After, by any ordinary reckoning, it should have already decided how to behave. When physicists actually built versions of this experiment, using clever arrangements of mirrors and switches to delay the choice of measurement until the last possible instant, the result held firm. Whichever choice was made, even after the particle's journey through the slits was technically complete, determined which pattern showed up on the screen. Choose to gather which path information, however late, and you get particle-like clusters. Choose to erase that possibility, however late, and the interference pattern reappears. It's as though the particle's past behavior adjusts itself retroactively to match a decision that, from an ordinary point of view, hadn't been made yet. Physicists pushed the strangeness one step further still with an experiment called the quantum eraser. Here, researchers mark particles with which path information as they pass through the slits. Enough, in principle, to know which route each one took. And then, after the particles have already struck the detector, use a clever trick to erase that information. When the erasure happens, the interference pattern comes back, retroactively, as though the particles never gave up their wave-like uncertainty at all. It's tempting and slightly dangerous to describe this as changing the past. It doesn't allow that. Nothing here permits sending a signal backward in time or altering an event that has already been recorded and locked in. The deeper, more careful reading is that quantum outcomes may not be settled by a single moment of measurement at all, but by the full, final arrangement of the entire experiment, including choices made after the particle's initial interaction. Some physicists describe this in terms of correlation rather than causation. The particle was never influenced by a future event. Rather, the complete pattern of entangled correlations across the whole setup only becomes meaningful once every piece, including the later choice, is accounted for. Others favor a block universe picture, in which past, present, and future all exist together as a single fixed structure, and what looks like backward influence is simply our limited, one-directional experience of a timeless whole. Whatever the correct interpretation turns out to be, these experiments make one thing unmistakably clear. Our ordinary intuitions about time, cause, and effect were built for rocks and coffee mugs, not for the quantum world. Down at that scale, the tidy one-way arrow we take for granted starts to blur. Not broken, exactly, but revealed as a special macroscopic approximation of something far less linear underneath. Part 9. The measurement problem. We now have all the pieces on the table. Wave functions described, in pure possibility, particles that only settle into a single fact when measured, and no clear answer for what a measurement actually is or why it forces a choice at all. This is the measurement problem, and for 100 years it has split physics into camps that cannot agree, not on the details, but on the fundamentals. The oldest and still most widely taught answer is the Copenhagen interpretation, shaped largely by Niels Bohr. Its central claim is almost defiantly simple. A quantum system genuinely has no definite properties before it's measured. Asking where an electron really was before you measured it isn't a hard question with a hidden answer. It's a meaningless question, because where only becomes a meaningful concept the instant a measurement happens. The wave function isn't a description of a hidden, pre-existing reality. It's a mathematical catalog of everything we can know, nothing more. Measurement doesn't reveal a fact that was already there. It creates the fact. Bohr never offered a grand explanation for why this should be true. His answer, in effect, was, physics tells us what we can say about nature, not necessarily what nature secretly is. This pragmatic shrug frustrated Einstein enormously. He wanted a universe that existed in full, definite detail whether or not anyone was looking, and the Copenhagen view struck him as saying the moon disappears the moment you turn your back on it. It has also become, half-jokingly, half-seriously, physics' unofficial motto for handling quantum weirdness. Shut up and calculate. The theory works. The equations are flawlessly accurate. Maybe that has to be enough. Not everyone accepted that. In 1957, a young physicist named Hugh Everett III proposed something radical. What if the wave function never collapses at all? What if, instead of resolving into a single outcome, every outcome happens, each one splitting off into its own separate, non-interacting branch of reality? Measure an electron's spin, and, in this picture, the universe doesn't choose between up and down. It splits. In one branch, you observe spin up. In another, an equally real version of you observes spin down. No randomness, no mysterious collapse, just an ever-branching tree of realities, all following the Schrödinger equation exactly, with no extra rulebook added on. This is the many worlds interpretation, and its appeal lies in its mathematical minimalism. It adds nothing to the equations, only removes an assumption. Its cost is almost unfathomable scale, a universe branching constantly at every quantum interaction everywhere, exponentially, forever. Critics point out that since the other branches are permanently unobservable to us, the theory is nearly impossible to test directly. Supporters respond that testability was never the goal. Simplicity was, and adding an unnecessary collapse rule to the math is the greater sin. A third path tries to make measurement itself less mysterious, not more. Decoherence doesn't propose new physics so much as it describes, in exhaustive and testable detail, what actually happens when a delicate quantum system meets the noisy real world. A particle in superposition is never truly alone. It's constantly bombarded by stray photons, air molecules, the ambient thermal glow of everything around it. The instant it interacts with any of them, it becomes entangled with its environment, and its fragile interference pattern bleeds outward into a vast, uncontrollable web of surrounding particles. Once that information has leaked into the environment, the interference is gone, not because a mind collapsed it, but because it's been diluted past any hope of recovery. This happens fast. A dust grain floating in ordinary air loses its coherence in a fraction of a second too small to picture. For an object the size of a cat, or a coffee mug, or a human being, decoherence is effectively instantaneous, complete before any observer, conscious or not, register a thing. This is the real physical reason you have never seen a table in two places at once and never will. Not because anyone is watching it, but because a large object simply cannot avoid entangling with the world around it for even an instant. Decoherence is a genuine triumph. It explains, with no appeal to minds or mysticism, why the everyday world looks solid, definite, and classical. A world without decoherence would be a world where superpositions never washed out, where the strangeness of the double slit leaked freely into daily life, where coffee mugs and coin flips carried the same ghostly ambiguity as a lone electron. That world does not describe our experience, and decoherence is the reason why. But even its strongest defenders admit it doesn't finish the job. It explains why you never see the cat in a blur of alive and dead. It does not explain why, when you open the box, you find this particular cat alive, say, rather than the equally well-defined dead one sitting in the other branch. That final step from a menu of separated possibilities down to the single actual outcome you experience still has no agreed name for its mechanism. Physicists call it, simply, the problem of outcomes, and it remains open. Surveys of working quantum physicists on whether the measurement problem is settled find no consensus at all. The community remains genuinely, professionally divided a century in. Sir. Part 10. Who is watching? If decoherence explains so much, why does the word observer keep creeping back into this story? Follow the logic one careful step further than most textbooks do, and you'll see why some of the 20th century's sharpest minds were tempted toward an idea. That sounds, at first, almost mystical. When we place a detector at the double slit, we say a measurement has occurred. But a detector isn't magic. It's just atoms, trillions of them, obeying the very same quantum rules as the electron it's trying to catch. So by the theory's own logic, the detector shouldn't collapse anything either. It should simply join the electron inside a larger, slightly bigger cloud of superposition. Now look at the detector's readout. But your eye is made of atoms too, and it should join the cloud as well. The signal travels up your optic nerve, also atoms, into your brain, also atoms. At every stage, by this reasoning, the haze should only grow larger, swallowing each new system rather than ever resolving into one plain fact. This chain of reasoning is named after the mathematician who spelled it out with brutal precision in 1932, John von Neumann. His conclusion was unsettling. The equations never tell you where this chain has to stop. You can draw the dividing line, the cut, between quantum haze and definite fact, almost anywhere you like, early or late, and the mathematics comes out exactly the same either way. The theory is simply silent on where the blur becomes a world. Von Neumann noticed something else too. There is exactly one link in that chain that never seems to end up in superposition: your own awareness. Whatever else remains uncertain, you never experience yourself as smeared across two outcomes. You always find yourself in one single, definite reality. And so a small number of serious physicists took the boldest step imaginable. If the chain has to stop somewhere, and the last uncollapsed link is awareness itself, then perhaps consciousness is what finally forces the universe to choose. It's a genuinely extraordinary proposal. For a moment, mind was not a spectator of the physical world, but its author. And it is exactly here that wonder runs headlong into a wall neither physics nor philosophy has ever fully cleared. We do not know what consciousness. Neuroscience can map which brain regions activate when you see the color red, trace the electrical cascades behind a decision, even predict some choices before a person feels they've made them. But every one of those achievements describes the machinery, the processing, the wiring, the behavior. None of it touches the deeper riddle. Why any of that processing should be accompanied by experience at all, why there is something it feels like to taste salt or see red rather than mere information moving silently through the dark. Philosophers call this the hard problem of consciousness, and it remains, quite genuinely, hard. Asking physics to build its foundations on the one thing science understands least turned out to be an unstable proposal, and within a generation, it largely collapsed under its own weight, not from a disproving experiment, but from its own internal problems. If only my awareness collapses the wave function, how do I know yours does too? The idea drifts uncomfortably close to solipsism, the claim that only one mind truly exists, a conclusion almost no one is willing to accept. No experiment has ever been devised that could distinguish a universe where consciousness causes collapse from one where it doesn't. The most damning of all, consciousness appears nowhere in the actual equations of quantum mechanics. Every experimentally confirmed prediction the theory has ever made can be calculated without writing down a single symbol for a mind. Even physicists who once championed the idea eventually walked it back, in part because decoherence offered a purely physical account of why the everyday world looks classical. No conscious or otherwise, required. The mainstream verdict today is blunt. Consciousness causes collapse is largely discarded by working physicists. As one put it, are we really meant to believe the universe hung suspended for 13.8 billion years, waiting to become real the instant some sufficiently qualified observer, perhaps holding a doctorate, finally showed up to look at it? And yet the deeper question the idea raised refuses to die quietly, because science has never stopped trying to catch consciousness in the act, using two very different research programs that, as of the mid-2020s, have finally been pitted directly against each other. One holds that awareness arises when information is broadcast widely across the brain, made available all at once to a global network of regions. The other holds nearly the opposite, that consciousness is a measure of how tightly information is integrated, how irreducibly woven together a system is, captured in a single mathematical quantity researchers simply call phi. And the landmark, pre-registered 2025 collaboration, hundreds of volunteers had their brains scanned while both theories' sharpest, most specific predictions were tested head-to-head, with the outcome criteria locked in before any data came back. The result crowned no winner. It supported part of the first theory's claims about where conscious content lives in the brain, while undercutting the second theory's insistence that the front of the brain has to be involved, leaving both frameworks standing, wounded, unconfirmed. Sit with that for a moment. We have split the atom. We have photographed the shadow of a black hole. We can predict quantum outcomes to 12 decimal places, and we still cannot say with confidence what it is that is reading this sentence right now, or precisely where inside your own skull that experience is happening. And part 11, 13 billion years before, and I append. Here is the fact that seems to demolish the consciousness collapse idea completely, all on its own. The universe is old, almost unthinkably old, and for nearly the entire span of that history, there was no one here to look at anything. Run the story from the very beginning. At first, there is no sky, because there are no stars yet to make one, only a searing plasma of bare nuclei and free electrons, so dense that light itself cannot travel through it, endlessly scattering. Trap. The universe, in its infancy, is luminous and blind at the same time. Roughly 380,000 years in, the plasma cools enough for electrons to be captured by nuclei, forming the first neutral atoms. And in that instant, light is finally set free to travel. That ancient light is still crossing space right now. We detect it as a faint background hum reaching us from every direction in the sky, the oldest image any instrument has ever recorded. A photograph of an infant universe taken before there was a single thing in it that could be called a thing. Then, real darkness. Tens of millions of years, astronomers call the cosmic dark ages, with no stars, no galaxies, no light being made anywhere, just hydrogen and helium drifting, cooling, gathering with excruciating slowness under their own gravity. Eventually, somewhere in that dark, a knot of gas grows dense and hot enough to ignite. The first star switches on, then another, then millions, a moment astronomers call cosmic dawn, when the universe finally lit its own lamps. Those first stars, brilliant and short-lived, forged the first heavy elements, carbon, oxygen, iron, out of raw hydrogen, then scatter that enrichment across space when they die, seeding every generation of stars, planets, and eventually bodies that would come after. Every atom heavier than helium in your body was cooked inside a star that lived and died before the Earth ever existed. When astronomers finally built telescopes powerful enough to look back into that first billion years, they expected small, faint, fumbling beginnings. Instead, they found monsters, galaxies far more massive and luminous than any model predicted, assembled only a few 100 million years after the beginning, in a universe that had barely had time to make them. The cosmos was already building grand structures, faster than theory said it should, long before anyone was around to admire the achievement. 9 billion more years pass in vast, silent cycles of stars being born and dying before a modest yellow star flickers to life in the suburbs of one ordinary galaxy, wrapped in a disk of debris that slowly clumps into worlds. One of those worlds is ours. It forms about 4.5 billion years ago, and it is still not alive. The first faint stirrings of life, single cells in a warm, dark sea, appear only around 3.5 to 4 billion years ago. Anything you could reasonably call a mind, anything capable of noticing, of asking a question, arrives only in the final sliver of the whole story. Compress the entire history of the universe into a single calendar year, and every observer who has ever existed shows up in the last few hours of the last day of December. Now lay that timeline over the mystery from the last chapter. If reality only becomes definite when it's measured, and if, as some were tempted to believe, that measurement requires an aware mind, then for 13 billion years, there was no one to do the measuring. No eye open, a question asked, and yet stars burned. Elements were forged in their cores. Galaxies turned. The very atoms that would one day become your brain were assembled in stellar furnaces billions of years before any brain existed to be assembled from them. How could the process that eventually built the observer have been waiting on that observer to make it real? The idea seems to devour itself. It's not that the cosmos hung suspended in an unresolved fog for 13 billion years, holding its breath, only to snap into focus the moment something warm and wet finally blinked awake and looked up. That isn't a universe. That's a stage set waiting patiently for its audience, and nothing in physics suggests reality is quite that needy. Physicists escape the trap several different ways, and it's worth laying them side by side rather than picking a winner, the simplest. Nobody needed to be watching because the whole paradox smuggled in an assumption, a conscious witness, that was never actually required by the theory. A subtler answer. Perhaps the cosmos was measuring itself the entire time. Every collision, every photon absorbed by a grain of dust, every interaction between one particle and another can play the role of a measurement in the strict physicist sense of the word, and the early universe was nothing but interactions, ceaseless and everywhere, at unimaginable density. On this view, reality never needed a spectator, because it was already drowning in measurement from its very first instant. Part 12. The oldest answerer. We followed physics as far as its equations can honestly carry us. What remains is a genuinely open philosophical question. Can existence exist without being known? And it's worth being completely honest about where we're headed next. Out of physics and into philosophy and theology. Nothing in this next section is predicted by any equation. Nothing here can be measured, tested, or confirmed in a laboratory. Hold that boundary clearly in mind, because it's the whole point of being honest. Here's the strange thing. Long before physics ever asked this question, humanity had already been circling it for thousands of years, across civilizations that never traded a word with one another, arriving again and again at a remarkably similar intuition. In the West, the 18th century philosopher George Berkeley proposed something that sounds, at first, like a child's riddle. To exist is to be perceived. And everything we've ever known about the universe, he argued, has come to us through perception. Every color, sound, and solid surface arrived as an experience in a mind, and reality simply is that experience, not some hidden substance lurking behind it. The obvious objection followed instantly. Does a tree in an empty courtyard vanish the moment no one is looking at it? Berkeley's answer became the direct ancestor of this whole documentary's question. No, because the tree is never truly unperceived. There is, in his view, always one observer present, an infinite mind that perceives all things, everywhere, at all times, and by that ceaseless perception holds the entire world steadily in being. Travel east, and you find a different route to a similar destination. In the philosophical traditions of India, thinkers spent millennia pressing on a single, simpler question. Watch your own thoughts arise and dissolve, your emotions rise and fade, and notice that something remains constant through all of it, some silent witness that notices every change without itself changing. They called it the Sakshi, the witnessing self, and made a striking claim. What you truly are is not the racing stream of thoughts and feelings, but the silent, unchanging awareness in which all of it appears. A screen never scratched by the film projected onto it. In its deepest form, this tradition holds that the ultimate ground of reality, Brahman, is itself consciousness, not something a brain produces, but the fundamental ground everything else appears within. The witness inside you and the witness beneath the cosmos are, in the end, the same witness. The great Abrahamic traditions arrive at a related intuition dressed in the language of a personal God, sharpened to a single point: omniscience. Nothing anywhere goes unobserved. And crucially, in classical theology, this is a claim not just about knowledge, but about existence itself. Creation isn't a single event set in motion long ago and left to run on its own. It is sustained, moment to moment, by the continuous attention of its creator, with the striking implication that withdrawing that attention, even briefly, would mean the world simply ceasing to be. A related, subtler idea, panentheism, holds not that God is the universe, but that the universe exists within God. The way a thought exists within a mind, contained by it, known by it, yet not identical to it. Even in the 20th century, this thread continued in secular philosophy. Alfred North Whitehead built an entire framework, process philosophy, around the idea that reality is made not of static, inert stuff, but of events, moments of experience woven together with something like a cosmic experience taking in and holding every fleeting moment as it happens, so that nothing that ever occurs is truly lost. Lay these traditions side by side. Berkeley's sustaining perceiver, the Vedantic witness, the omniscient God of Abraham, Whitehead's cosmic experience, built centuries and continents apart by people who never read each other's work, and they converge again and again on roughly the same shape. An awareness that doesn't depend on being born, occupies no single location, never begins, and cannot end. It would be dishonest to leave the objection out of the story, because it's a serious one. Many thinkers reject every version of this idea, and their case is sharp. The fact that so many cultures independently reached for a cosmic witness may say far more about the structure of the human mind than about the actual structure of the universe. We are storytelling creatures whose every experience is centered around a watching self. We've never known existence from any vantage point except the inside of an aware mind. So when we imagine the vast unknown, we naturally populate it with a presence, not because one is there, but because it's the only way we know how to imagine anything at all. Similar answers across cultures need not point to a shared truth. They may only reveal a shared psychology, and an idea being ancient, comforting, or nearly universal has never once, by itself, made it correct. That objection deserves to stand exactly where it lands, unresolved. None of this is what quantum mechanics says. The equations contain no God, and countless physicists build entire careers predicting nature to staggering precision without ever needing one. What these traditions offer isn't a competing scientific hypothesis, it's a proposed answer to a different, stranger question sitting underneath the physics. Not how does the world behave, but Why is there a definite world here to be described at all? It's part 13. What is the universe made of? For 4 chapters, we've circled one question: who or what is doing the watching? Now turn the question inside out. Forget who's looking. Ask instead, what exactly is being looked at? What is the universe actually made of? The natural answer is matter. Solid stuff assembled into bigger stuff. Wrap your knuckles on a table and it answers back, hard and undeniably there. But push down past the table, past the molecules, past the atoms, to the smallest scale physics can describe, and the solid stuff quietly disappears. What's waiting at the bottom isn't a miniature pebble, it's the wave function, that spread of possibilities we met at the very start. And the wave function is not, in any ordinary sense, a substance. You cannot hold it, weigh it, or point to where it physically sits. It is, in the most literal sense, a ledger. An exact accounting of what might happen and how likely each outcome is. It is information. That realization gave rise to an entire field, quantum information theory, which stopped asking what particles are made of and started asking what they can know, store, and transmit. And as physicists began rewriting the quantum world in the language of information, they found something almost eerie. Nature guards its information with an accountant's obsession. Quantum information cannot be perfectly copied. It cannot, according to our best current understanding, be truly erased. Push it into the most destructive object known, a black hole, and physicists now believe even that cannot annihilate it completely. The universe keeps its books with fanatical care. Nothing is ever fully lost. The physicist who saw furthest down this road, decades ahead of most colleagues, was John Archibald Wheeler, the same man who coined the term black hole. Late in his career, he distilled the entire vision into 3 words that still ring through physics today. It from bit. Every particle, every field, every object you have ever touched, he argued, derives its existence, in the end, from answers to yes or no questions posed to the world. Reality doesn't bottom out in matter. It bottoms out in information. A pattern, a code, a vast self-consistent web of answers, with matter as merely its visible surface. Then physics found something that made Wheeler look less like a dreamer and more like a prophet. When physicists calculated how much information a region of space can possibly contain, they expected the answer to scale with its volume. The bigger the box, the more you can pack inside, exactly like everything else in ordinary experience. That is not what the mathematics said. The maximum information any region can hold turns out to depend not on its volume, but on its surface area, the boundary wrapped around it, not the space within, as though the true bookkeeping for any chunk of the universe actually lives on its outer skin. That single strange fact grew into the holographic principle, the suggestion that the 3-dimensional world we move through, with all its depth and solidity, might be something like a projection. Everything happening inside a volume of space fully encoded on a lower dimensional boundary surrounding it, the way a flat holographic plate, lit correctly, throws up a full 3-dimensional image. It remains a powerful theoretical framework, not an experimentally confirmed fact about our actual universe, worth holding loosely. The frontier goes further still, into territory genuinely unsettled and still being fought over in the research journals. A significant body of recent theoretical work suggests that space-time itself, distance, geometry, the very fabric general relativity describes, might not be fundamental at all, but woven out of quantum entanglement, with space and time emerging from the entanglement of countless tiny bits of information. Tighten the entanglement between 2 regions, and, on this view, they draw nearer. Loosen it, and they drift apart. Cut it entirely, and the space between them simply ceases to be. If this holds up, space and time aren't the stage the universe performs on. They are the performance. What a deeper layer of pure information looks like once enough of it is entangled together in the right pattern. the way temperature emerges from the blind jostling of countless invisible atoms underneath. It's worth pausing on how extraordinary this shift really is. For 2,000 years, philosophers argued over whether reality was ultimately made of earth, water, fire, atoms, fields, or energy. Every candidate a substance, some ultimate stuff the world was carved from. Almost none of them imagined the deepest answer might not be a substance at all, but a relationship. Not a thing, but a pattern. Which leads straight back to the question wonder keeps circling. Information, everywhere else in our experience, needs somewhere to live. Words need a page. Music needs a groove or a file. A memory needs a brain. So if the universe is, at bottom, information, where is it actually written? What is the page beneath the page? Most physicists would answer plainly. Information doesn't need a reader any more than gravity needs an audience. A spin can encode information whether or not anyone measures it. A black hole can preserve information whether or not anyone ever works out how. On this view, information in physics means objective structure and correlation, a fact about the world, full stop, with no implied reader required, no more mysterious than the bare existence of the number 7. And yet that tidy answer leaves something quietly unresolved, because ordinary language uses the word information to mean something else entirely. A message that lands somewhere and matters to someone. Whether those two meanings, the physicists and the everyday one, are ultimately the same thing, or only share a name by coincidence, remains a genuinely open philosophical question, one physics has never had to settle because its predictions never required the second meaning to come out correct. Part 14. The skeptic's case and the door it leaves open. Fairness is the whole soul of science, and so, having followed the road this far toward wonder, it's time to hand the floor to the people who think every step of the last several chapters took a wrong turn. They hold the strongest hand at the table, and honesty demands we say so plainly. The skeptic's case starts by returning to the word that began all of this: observation, and asking whether it was ever as mysterious as it sounded. The entire mystery rested on an intuition that something special, almost magical, happens the instant a measurement occurs. But what if measurement is nothing but an ordinary physical process, one we can now describe in exhaustive, unmysterious detail? We've already met that process. It's decoherence, and to its strongest defenders, it is the quiet demolition of the entire paradox. In the pristine thought experiments, we always imagine a particle drifting alone in its delicate haze of possibility, undisturbed. But in the real universe, nothing is ever truly alone. Every particle is ceaselessly bombarded by stray photons, air molecules, ambient thermal radiation, the faint hiss of the cosmic background itself. The instant it brushes against any of them, it becomes entangled, its fragile wave nature bleeding outward into the environment's uncountable degrees of freedom. Once that information has leaked outward, the interference pattern, the unmistakable fingerprint of quantum possibility, is washed away automatically, blindly, with no mind, no God required anywhere in the process. And the scaling is decisive. The bigger the object, the faster this happens, not gradually, but catastrophically fast. A single floating dust grain loses coherence in a sliver of a second too small to picture. For a measuring device, a cat, a human being, decoherence is effectively instantaneous, complete before any conscious creature could possibly notice. This is the actual physical reason you have never seen a coffee cup in two places at once, never caught a cat suspended between life and death. Not because anyone happened to be watching, but because a large object cannot avoid entangling with its surroundings for even an instant. The world is measuring itself everywhere, trillions of times each second, with no observer, no eye, and no awareness required anywhere in the machinery. That's a formidable case, and it may well be correct. But even this account leaves one corner of the room untouched, and an honest telling has to say so. Decoherence explains beautifully why the world always looks classical and definite. It does not explain why, in any single run of the experiment, you get this particular outcome rather than the other. Decoherence takes the ghostly blend of alive and dead and separates it cleanly into two fully formed, non-interfering possibilities. What it never tells you on its own is which one you'll actually find when you open the box. That final step, from a menu of separated possibilities down to the single actuality you experience, is the problem of outcomes, and it remains genuinely, stubbornly unresolved, which is exactly why the many worlds interpretation exists. Rather than assume the universe deletes one branch, why not assume both simply persist, forever separated, with you riding along just one of them, unaware of the rest? It's a formidable answer. And notice, before we move on, what even this triumphant account has quietly left standing in the corner. Neither decoherence nor many worlds explains why there is a definite experience at all, why you open the box and meet one particular cat, why there is one specific world you actually find yourself inside, rather than a bookkeeping abstraction spread thinly across countless branches. The hardest form of the question slipped through the net while everyone was admiring the size of the catch. And that raises a strange, almost liberating suspicion. A century of the finest minds who ever lived has failed to close this gap. What if the reason isn't that the answer is too hard to reach? What if the question itself was shaped wrong from the very start? What if we've spent 100 years hunting for the observer as though it were an object hidden somewhere inside reality? A mind, a machine, a god at the edge of the universe, when every candidate we've caught has either dissolved on inspection or turned out to be unnecessary. Follow that thought all the way, and you land in the oldest trap in philosophy. Suppose reality really does require an observer to become definite. Fine, but an observer is itself something that exists. So what makes the observer definite? Another observer watching the first. And what makes that one real? You've started an avalanche that cannot stop. Observer behind observer behind observer, a hall of mirrors receding into infinity. Philosophers call this an infinite regress, and it's fatal to any theory that tries to explain existence by pointing to yet another existing thing, because every answer just relocates the question one step back and asks it again. There is exactly one way the regress can ever close. Not with a final observer watched by some further observer, but with something that observes itself. Something that is, at once, the seer and the seen. And we already know of precisely one thing in the entire universe that does this. You, right now. Awareness is the one phenomenon that can turn back on itself, be conscious of being conscious, hold itself as its own object without needing anything outside it to do the holding. Wherever the chain of observation was always going to have to stop, it could only ever stop there. Which reframes the entire question one final time. You are built from atoms forged inside ancient stars, scattered across the dark, gathered into a world, and assembled over billions of years into a creature that can look up at the very sky those stars once lit and understand what it's seeing. Structurally, that means something specific. You are a piece of the universe, and you are aware, which means the universe, through you, has become aware of itself. For 13 billion years, matter rearranged itself quietly in the dark, and then, in you, and in every conscious being since, it began, in some small local way, to know that it exists. In closing, what is doing the knowing? We started with a pattern of light on a screen, 2 slits, a scattering of dots that shouldn't have added up to anything, and somehow did. We're ending at the threshold of the deepest question a mind can ask: can anything exist at all, independently of being known? And beneath even that sits a question with no floor beneath it at all, the one philosophers have asked for 3 centuries and never answered. Why is there something rather than nothing? We don't know. And having followed the road all the way to its end, The only honest thing left to do is lay the possibilities side by side, refuse to choose on your behalf, and let you stand exactly where every person who has ever taken this question seriously eventually has to stand, alone with the mystery. The first possibility is the simplest, and it may well be true. Reality is entirely, exhaustively physical. Consciousness is a remarkable but ordinary product of the brain, an intricate pattern of matter that switches off completely when the matter stops. The universe ran for billions of years without a flicker of awareness and got along perfectly well without one. There is no cosmic witness, no eternal observer waiting in the wings. Only the vast, elegant machine, and we are a fleeting arrangement within it that briefly lit up, asked why, and will one day go dark. It is a stark picture. It is also, by a wide margin, the most economical one, and economy is a virtue science has earned the right to insist on. The second possibility inverts the whole picture. Consciousness isn't produced by matter. Matter emerges within consciousness, the way a landscape arises inside a dream without the dream being made of soil and stone. On this view, the universe is, at its deepest level, more like a mind than a machine, and we are not devices that happen to generate awareness, but awareness that dreamed up the appearance of devices. It sounds mystical. It also solves, in a single stroke, the one problem the purely physical picture has never touched: why there is any experience here at all. The third possibility is the oldest and the boldest of the three. There exists an eternal observer, not a being among beings, not a force hiding somewhere in the equations, not anything a telescope could ever find or an experiment could ever detect, not required by the mathematics. The mathematics runs perfectly well without it, and yet perhaps necessary for a reason mathematics was never built to reach. Not to explain how reality behaves, but why there is a reality here for the equations to describe it all. An awareness that never began, holding existence in being simply by knowing it. The witness that finally closes the infinite regress, not by being watched itself, but by being the one thing that needs no watcher. Three answers, one universe. And in principle and in practice, not a single experiment that can tell them apart. This is where physics ends and where you begin. Perhaps the greatest discovery to come out of a century of quantum physics was never that particles behave strangely. It was that the universe, in the end, forced us to ask a question science had assumed it left behind long ago. What does it mean to observe? What is this awareness we each carry every day of our lives and still cannot explain? Why does reality come in a form that can be known at all, rather than sitting forever in the dark, unwitnessed, and unaware that it's even there? Whether the true answer turns out to be physics or philosophy, or something neither discipline has fully named yet, one plain fact will still be waiting long after this ends. The deepest mystery in the universe may not be hidden out among the stars, or buried in an equation, or lost somewhere in the first instant of time. It may be much closer than that. It may be the awareness reading these words right now. So we leave you not with an answer, but with the same question that started everything, the one you're now holding entirely on your own. Think back to where we began. A wall, two slits, a single lonely photon crossing an empty apparatus with nothing else around it to interfere with. And somehow, impossibly, interfering with itself anyway. From that one small, almost laughably simple result, everything else in this story unfolded, the way a single loose thread, pulled gently, can unravel an entire sweater. We watched Max Planck patch a stubborn equation without believing his own patch, and watched Einstein take that patch seriously enough to show that light itself refuses to be only one thing. We followed Schrödinger's equation down into the atom and found electrons weren't tiny orbiting planets at all, but standing waves of pure probability. We sat with Heisenberg's uncertainty, not as a failure of measurement, but as a fact woven into the architecture of the world. The very thing that keeps atoms from collapsing, that gives matter its shape and its stubborn refusal to be pinned down completely. We met particles that are neither purely wave nor purely thing, cats that are neither purely alive nor purely dead, and empty space that is never purely empty. We traced how those same strange rules, once confined to chalkboards and laboratories, quietly slipped into the phones in our pockets, the lasers in our checkout scanners, and, if a small, stubborn field of researchers is right, into the compass sense of a migratory bird and the first flicker of energy inside a leaf. Then, at the center of all of it, we kept running into the same closed door, the measurement problem. A century of the most disciplined, most rigorous thinking our species has ever produced, and still no final consensus on what happens in the instant a cloud of possibility becomes a single, definite fact. Copenhagen tells us not to ask. Many worlds tells us the question dissolves if you're willing to accept an unimaginably large universe. Decoherence tells us the fog clears itself silently, automatically, everywhere, all the time, with no need for anyone to be watching at all. And yet even decoherence, for all its explanatory power, cannot tell us why you experience one single particular outcome rather than a menu of separated possibilities. It would be tidy to end there, with a shrug and a nod to the equations, the way so many physics documentaries do. The math works, and maybe that has to be enough. And for the purposes of building a laser or a transistor or a quantum computer, it genuinely is enough. But we followed the question a little further than that, out past the edge of what any experiment can settle, into the oldest conversation our species has ever had with itself. Whether the universe was ever, even for a moment, truly alone in the dark. We are not asking you to believe any particular answer to that question. Science can't hand you one, and this documentary was never going to pretend otherwise. What we can offer instead is something quieter and maybe more useful. The plain, well-earned fact that the smartest people who have ever lived, working with the best tools our civilization has ever built, looked as hard as they possibly could into the heart of matter and found not a solid floor, but a shimmering, open question. That isn't a failure of physics. It might be the most honest thing physics has ever told us about itself. There's a strange comfort hiding inside that uncertainty if you're willing to sit with it a little while. We like our answers clean. We like cause leading tidily to effect, evidence leading tidily to conclusion, questions leading tidily to answers we can file away and stop thinking about. The quantum world was never going to give us that. And maybe, in its own strange way, that's a kind of gift. A universe that had already answered every question about itself would have nothing left to discover. A universe still asking, still shimmering, still holding its deepest mystery just out of reach. That's a universe still worth exploring. And you are, this very moment, a part of exactly that unfinished exploration. Consider, for a moment, what you actually are physically, right now, listening to or reading these words. Every atom heavier than hydrogen in your body was forged inside a star that lived, burned, and died long before the Earth existed. The calcium in your bones, the iron in your blood, the oxygen you just breathed in, all of it assembled over unthinkable stretches of time, out of the same quantum fields we described a few chapters ago, rippling, humming, uncertain all the way down. You are not really separate from the strangeness this documentary has spent so long describing. You are made of it. The same uncertainty that lets an electron tunnel through a barrier it shouldn't be able to cross is, in some very literal sense, the uncertainty that lets your own atoms hold together at all. If quantum mechanics leaves us anywhere, it leaves us here, in a universe that is far stranger, far softer at the edges, and far less finished than the tie-dye clockwork picture physics inherited from the 19th century. A universe of probabilities rather than certainties, of relationships rather than solid little things, of questions that have outlived every mind that has ever asked them, and will very likely outlive ours as well. If reality only becomes real once it is known, then what exactly is doing the knowing?